Welcome, everybody. Glad to have you this afternoon. It's great to be getting together for another boot camp. Something I really missed. I was on boot camp withdrawal with pangs. All right. But today we're going to be talking about different kinds of caches and buffers that are located in various different places within OpenVMS and how we can utilize those to improve performance of our OpenVMS applications. There are various different places that your data can be within VMS. It may start out on a disk and end up in the CPU's cache, but it's got to go various different places along the way. So data can be stored in the CPU, it can be stored in memory somewhere, or it can be located in some sort of storage device. And in general, we all know that as we go from the CPU out to the storage device, we get increasing capacity, decreasing cost for each byte that's stored, a decreasing data transfer rate. So you can get stuff from CPU caches into the CPU very quickly, but to get it from your disk, it's going to be slower out there. And the latency to get to the data decreases as you go from the CPU out to memory, out to the storage device. But those are things that you all do anyway. Within the CPU, you may be looking at virtual address translation buffers. That's where we cache address translations for virtual addresses so we can get to them faster. We may have instruction cache for the instruction stream, data cache, and in the CPU, we may also have a couple of different hyperthreads running that have context of what's going on. Within memory, we might have data associated with the file system. So we've got buffers or caches associated with file system contents. Some sort of data manager might be involved. You might have a database, you might have RMS, something like that, cache, or you can store data in your actual application. I remember looking at a program that somebody had written once, and they were reading a little indexed file. The indexed file only had about 6 or 7 records in it. But every time they needed to know whatever the translation was, they were going to the file and reading the record. And as a programmer, I was thinking it would be a lot simpler to just read that small table into memory once and access it from there rather than going out to the disk every time. So there can be caching of data in your application itself. Earlier this morning, one of the presentations was talking about how DCL, as it runs through a DCL command procedure, rereads a record of that command procedure, as if you were going to change that on the fly while you're running the procedure. No, it was rereading the line, and you think, well, just bring a bunch of DCL lines into memory and access them from there. Would be a lot more efficient. But your application can store the data itself, and then within a storage device, you may have levels of storage. You may have cache in the controller where blocks that you have read might be stored, or maybe blocks that you are writing are stored there in non-volatile cache on their way to the physical storage device. The storage devices often have cache. That may be read cache, or you can also turn on a feature where you write into that cache and then the storage controller takes its sweet time to write it to the actual storage device surface, whatever that is. It may be a surface of a rotating disk, or maybe SSD or something. And of course, the physical storage media where that is stored, which might be bits of magnetic material, or these days it's probably solid state disk. All right, how do we apply these? How do we apply optimization techniques in OpenVMS to each of these storage levels? Here are some ways we can do that. Within the CPU, to optimize virtual address translation buffer efficiency, we may use huge pages. That's where you map a large amount of contiguous space, both contiguous physically as well as contiguous virtually. Map those with a single translation buffer entry. So that allows us to map a lot of memory with just the one translation buffer entry. So the odds of that being in the CPU's list of translation buffers is higher because it maps so much memory. So we can use reserved memory to map areas of memory from the time we boot and keep it there. Non-page pool. If we allocate all the non-page pool that we need at the time that we boot, we don't have to extend it later. Now, a non-page pool, VMS will happily extend as you go on, but those pages that it's adding to the non-page pool later on aren't mapped to the initial huge page. So access to those areas are going to be a little slower because on the average, you may have to do a translation buffer fault, pull in the translation buffer entry for mapping that new data.
Is the whole many questions or just the area?
Just iterate.
So the reserved memory, you also get contiguous memory as well, right?
Right.
So if you know you need it, grab it at a time.
Yeah. Yeah.
Access C cache.
Yeah. With regard to the CPU instruction cache, if you use FastPath to assign the interrupts from devices to CPU to a CPU, and you assign devices sharing the same device driver to the same CPU core, then when an interrupt comes in from one of those devices, chances are greater that the interrupt routine for that particular device is already in that CPU's cache. VMS by default tends to spread devices of the same type across a whole bunch of different CPUs. Well, the interrupt state routine might be in a CPU on a different cache, but the odds are much better that it's going to still be in the cache when an interrupt comes from that a device of that type, if you direct the interrupt state work for all of those like devices for the same CPU. In terms of the data cache, if you've got device drivers that are passing packets back and forth among each other, then you may have that data in the CPU cache. You can pass it on off to another thread on the same CPU rather than passing it to another CPU for handling that. So that's another area where we can help. In terms of hyperthreads, we can enable or disable hyperthreads. We can use FastPath. We can turn the co-thread CPUs on and off. That can be ways that we can affect how those. And I addressed that in more detail in my other presentation earlier yesterday. All right, next at the memory level. File system, you can use ACP caches to cache file system metadata in memory. You can use XFC to cache file contents. The install utility can cache various things to speed image activations. You can say, go ahead and open the file and leave it open so you don't have to open it each time you're doing image activation. You can say, make the file header resident. Go ahead and read the file header for that image into memory and keep it in memory so you don't have to reread that every time the image is activated. You can make the header shared among multiple processes, and you can even tell it, make the whole image resident in memory so you don't have to read the image in when you do the image activation.
On the ACP caches, so
yes.
When you aren't using feedback in AutoGen, I get the feeling that it significantly underestimates those figures. I don't know whether you'd agree with that.
I think so as well, and I think people don't often do that. So I developed a tool that looks all of those, and I can give you the rules of thumb that I use to size those over time. That's one of the things we'll address. Okay, data managers, which might be databases or RMS. The number of local buffers that you use, the number of global buffers that you use can make a great deal of difference in performance. You can tell RMS to do read ahead and write behind caching. In the database area, you've got all sorts of options there for global buffers. You can use row cache. That can greatly improve performance. Some people will take an area of memory and turn it into a disk, a memory disk. Use that for faster access to storage. And of course, data caching can be done within your programs for if you have to read something frequently, putting it into memory and accessing it from there can help. All right, within the storage device, one of the things we'll look at is you can set the disk device cache to write back if you want to. That would be only for data that you can easily recreate, because if you have a power failure between the time that you write it and the time it actually gets onto the disk, that data could be lost. So you need to have some way to recreate that. But if you had maybe a compile link cycles or something like that, where you wanted just the fastest, or what was
Because it compiles over.
sort work temp files, where if the thing fails, if the power fails, you're gonna have to do the sort again anyway. So those sort work temp files could be on a disk where you're allowing the disk to write it to the actual surface whenever it gets written to it. But that's something you can use as a performance optimization when you understand what are the volatility requirements for that particular type of data. All right. The basic principle is that while data from a disk can be delivered into memory via direct memory access, and that's something that doesn't cost you CPU time because you're setting it up to begin and the hardware is doing the actual data transfer. If you're getting something from a cache, you're going to have to transfer that using CPU cycles from its cache area. You're going to have to search for it, find it, and then copy the data. The hardware's not going to be able to do that for you. Your CPU is going to be doing that. So that's going to be taking CPU time, which is bad. But if your CPU would have been waiting around for an IO anyway, using that CPU to actually move the data doesn't hurt, and your overall performance, your overall latency, response times would be better. So that's the basic idea that we're working with here. Huge pages are physically and virtually contiguous address space. It takes fewer virtual address translation look-aside buffer entries to map that. Basically 1. So the chances of a translation buffer fault are going to be lower, and the memory access is thus, on the average, a little faster to do that. I remember when was it Dick Seitz was the alpha designer, he decided that programmers shouldn't need more than 7 translation look-aside buffers. And that was all you should require, because he looked at all the different possible combinations. I know later versions of the alpha chip had a lot more translation buffer entries, but he was a purist and said, if this thing is going to run as fast as it can run, 7 is all you need and 7 is all you get. So, but it didn't turn out to be practical. Dax had, of course, thousands. So anyway, this is the way that we improve performance. So as I said, make sure your non-page pool is sufficient so you don't have to expand it at runtime, and you'll get just a little bit faster performance than if you're sloppy and it expands every time you boot. That's just sort of proactive system management, paying attention.
And where does list pre-prop of that fit into the on-page pool, or is that something still around? Has it gone away?
That's a good question. Look-aside list pre-population?
Yeah.
I don't know. I hadn't thought about that for a long time. Maybe it would be a good thing to look into if you find your system needs to. Yeah, that's a good question. I do not know. I'd have to study that a little bit.
What was the question?
His question is, he's saying you can pre-populate look-aside lists for non-page pool.
It's called list pre-prop dot that. And maybe it's back in, it's done a long time, so maybe it's back in history, maybe it's gone away.
Yeah, we just never goes away.
Yeah.
Sometimes things like the XFC task where we create a database, we know it's going to be accessed randomly, but we'll go through and scan a storage area, like basic, we publish that into the XFC section, and the application has going and everything's loaded. Big cost, but huge benefit. Yeah. Going to tie into that, we'll often use the memory reservation for XFC, so we get a contiguous chunk tree allocated. And
that's what this last point says. XFC by default can use up to half of memory, half of physical memory, if there's enough free memory and there's enough demand for XFC to do that. You can raise the maximum. We'll look at that in a moment. We'll move right to that. So XFC caches the contents of files. Directory files aren't cached by XFC, though they're cached in the directory index cache and the dir cache of the ACP caches instead. One of the nice things about XFC is it can do read ahead if it detects that you're doing sequential file accesses. So you're reading sequentially the same size IOs. It will go ahead and prefetch ahead of time and potentially get your data before you need it, before you make the next request. So that's a good thing. It also caches file control blocks. So if you open a file, close a file, that closed FCB will be cached by XFC. And if you reopen the file, then it doesn't have to do all of the work that it would have had to do otherwise because the FCP is cached. Another great thing about XFC is it keeps good statistics for you're monitoring your IOs. You can see what's a hot file. That's something that's very handy that came out of XFC. One thing it cannot do, though, is if you have files that are open for a write simultaneously on multiple nodes in a cluster, that is something that's beyond its capability. Some of the third-party LVM caches could solve that problem, or you can use RMS global buffers to solve that sort of a problem. But that's an area that was weak for, now XFC was much better than VIOC. Great improvement, but that's one weak area. So if you've got a file that's open for write and multiple nodes in the cluster, it won't be able to effectively cache that file well. Okay, by default, it uses up to 50% of physical memory with the default parameters, and it'll automatically free up memory when there's a shortage of memory. That's a nice thing, because if you have a bunch of stuff fire off and it needs a lot of memory, XFC will give that memory back to it and you don't run short. Now you can increase the maximum size using the sysgen parameter VCC_max_cache. We've had some customers where they need to load a large file and just pound on it. They might need more than half of physical memory to do that. If that's the case, you can raise the maximum, and when XFC needs it, it can allocate more space. That particular customer, 3/4 of their physical memory would nicely cache that file, and if that's what it takes, then you can take advantage of that. You can also set a minimum size using a reserved memory, and as Greg mentioned, this will be contiguous memory in both physical and virtual space for XFC to use. The one downside of this, though, is that is memory that XFC is unable to give back to the system. So it's allocated to XFC permanently. We had a customer system where mistake was made at boot time and allocated more memory space for other reasons, and memory got very short, but they had permanently allocated half of physical memory to this purpose, and it was not available. The system had to be rebooted to correct that problem, where if they hadn't reserved all of it, maybe if they'd reserved 1/4 of the memory, then half of the XFC memory would be efficient and half of it wouldn't, but you'd have some more resiliency, more flexibility if you needed to get that memory back.
This is still the floor, and it would still go up to the max cache above that.
Right, and that it can be flexible on it and give back. It's just that whatever you reserve can't be given back if the system gets. And if your system is stable and you are not going to need that for anything else except for XFC, fine, go ahead and reserve it. But whatever minimum area reserve will be a little more efficient to access fewer translation buffer faults. When should you avoid using XFC? Well, for data that you're not likely to read soon, because it's a read cache. So maybe you've got a large sequentially processed file. Maybe it's a backup save set that you're writing to. When you're writing it out, it's not going to be reread until the next time you need to restore something. So keeping that in memory in XFC to help you out is not going to be of any benefit. Maybe you've got a log file that's being written by the batch job. The only time you're going to read the log file is if the batch job fails. So that might be something where you really don't want XFC to keep it around and waste memory because you're not going to read it except once in a blue moon. How do you control this? Well, you can do set volume / cache equals no data. You don't want to do set volume / no cache, because if you do set volume / no cache, that also disables the ACP caches for the rest of the files on that. So you can do set volume / cache equals no data. And that just disables XFC without disabling ACP caches. All right, you can also set file / caching _ attribute equals no _ caching. And that will allow you to turn off caching on individual files if you don't want to waste the XFC cache in those files. You can also specify a maximum size. And you can say, if I'm writing something that's bigger than such and such a size, don't bother to cache that. So that's another knob you can use.
What we do is set volume cache equal no data, it dumps out whatever's in there, right? So isn't it better to do the set file caching attribute? To control your example, like the safe set and like.
Yeah, if you know that this file is only, I mean, this whole volume is just stuff that I don't. Maybe it's only backup save sets. I don't want to catch anything on that data because that's the target of my backup save sets. That would make sense.
Records.
Sorry.
We're setting on record.
Yeah,
Log files or.
set this attribute, this caching attribute, so that all files in that directory will have that attribute. It's also a handy tool to identify hot files. If you want to know which files you need to concentrate on in terms of performance, you can say show memory / cache equals, and then you can specify a volume, whatever particular disk device. You might want to say, what are the files that I'm hitting the most with QIOs? So give me a list of the top 5, so you can get the list. Top QIO equals 5. This would be as if I did top QIO equals 1. So here's the fact. Here's a write list is busy on this particular disk. That's an example. And it'll tell you how many read hits you're getting, how many read aheads, virtual reads, read throughs. What's the hit rate? That might be a lot of interest. I'm getting 98% hit rate on that, so that's pretty good. Pricelist.dat you can also set some global buffers on. RMS global buffers, that's nice. Because then all the processes can benefit from that. All right, there's also an SDA extension XFC that gives you statistics about XFC. So if you do in SDA, you'll do analyze / system to get into SDA and do XFC. For example, show volume / brief. Here's the sort of display that you would get. So you've got some useful things like what's the average response time? How many IOs are you doing? Which are the busiest disks? Where are you getting the best hits? So what for hits, how quick can you get a response? If you get a miss from the disk, how long does it take to get it? What's your average response time in milliseconds? Useful stuff.
Does it work on LD drive as well?
LD
Or
drives?
Yeah,
Yeah, it should.
okay.
It should. Should work on any disk volumes that are mounted. It should work on. I suspect if you do set volume / cache equals no data, you probably won't get useful data. All right, ACP caches. We've mentioned this before. They hold file system metadata, and higher hit rates can increase performance. What I like to do for a rule of thumb is to aim for a hit rate of 95% or better. And if you're getting 95% or better hit rates, you're probably doing okay. Sometimes you'll see 98, 99. That's fine. If you want to devote a little more memory to it, get a little better higher hit rate, that's fine. But a great way to look at this is in SDA, do clue memory / statistic, and it'll tell you each of the ACP caches, what their current size is, how many hits, misses, and people will even calculate the hit rate for you there. So here, the final hitter cache, I'm only getting 88.8%. So I'd like to get that a little high. Sometimes I'll see some of these down in the 40, 50% range. You can definitely get some improvement out of that. Storage bitmap cache at 89.5. I could probably raise that a little bit. Directory data cache, 98.8. I probably don't need to raise that much, because, if any, because it's already doing so well. 99.6 on directory recently used cache, the directory index cache. At 99.6, there's not much to complain about, and even less for the FID cache at 99.9%. So devoting more memory to that is probably a waste of my time. Quota cache shows up as 0% down there at the bottom. That probably just means that disk quotas are disabled. So if you're not using disk quotas, that's just a data point to ignore. Don't worry about the fact that you're getting 0% hit rate if you're not doing any accesses for that. All right.
This also obviously shows up in AutoGen when you run it. The stats, right?
Yeah, as Nick was pointing out, AutoGen, I don't know that AutoGen does a very, I'm sorry?
the percentages are correct, aren't they? You know?
Yeah, the percentages in Autogen are correct. I think Autogen rounds it. It either truncates it or rounds it in terms of percentages, but it's very, Autogen is obviously using the same data to tell you what it's getting. But I haven't found Autogen to do really a good job of resizing these. So I like to resize them myself. All right. The ACP caches reside in the paged pool. This means if you don't have enough space in virtual memory, they can be paged out to your page file, so that's fine. So if you get them too big, it's not a problem in terms of physical memory. But they are potentially a problem in terms of running out of paged pool. So you want to keep enough paged pool available that if you raise these, you'll have enough space to still fit them within the paged pool. Page pool is controlled by the sysgen parameter page time. That's a static sysgen parameter, so to raise it is going to require a reboot. So if you raise the ACP caches and you run out of page pool space, you're talking about a reboot to raise the page pool space. So I like to keep some extra, and I like to also bump it up when I raise the ACP cache sizes. I like to keep the page pool utilization below about 2/3 used, just so I've got some headroom. Just like global sections. I like to keep global sections and have some, since it requires a reboot to change it, I like to have some headroom. That's another example of that. Now, if page pool space is short when you mount a disk, VMS will allocate what are called minimal ACP caches. That's not good for performance on that disk. The reason the way you can tell that that has happened is you'll see a very low number for the maximum buffers in FCP cache. And I've gone onto customer systems and found that this is the case, typically because the system manager has said, well, I'm getting low hit rates on the ACP cache. I think I'll raise that. Well, after the next reboot, he's still getting low hit rates because he's got minimal caches. He's probably getting even worse hit rates. And so if you do a show device D/full and search that for maximum buffers in FCP cache, that can tell you whether you've got any of the volumes that are mounted this way. Now, if you have volumes that are mounted with minimal ACP caches, you probably need to raise the size of the page pool and then reboot. This can happen often when people are seeing low hit rates on them ACP caches, and so they bump everything up, then an Autogen do a reboot, and don't notice that they didn't have enough of the paged pool. So that's something to watch for. And like I said, I've seen this in customer systems where they didn't even know that this was happening until we came along and looked at it and said, well, wait a second. If you're running into this problem of not having enough page pool to allocate the size of ACP caches that you want. Now, that number is normally 5 times the balance set slot count. So if you have a balance set slot count of, balance set count of 1,000, that should be at least 5,000. Those are going to be much larger numbers on most OpenVMS systems. So a small number like 24 means you've got a problem. Another problem that we run into, I'd love to see VSI change this. Cache size for ACP caches is a 16-bit field, but that means their maximum is 65,535. If you're trying to set a larger value, you can get away with setting a larger value. You can go into sysgen and say, set it to 200,000, whatever you want to set it to. But what really happens in practice is that gets truncated to 16 bits and gets stored. And so it will be your value modulo 65,536. And I've done that before. I've raised it to above the value. And sysgen says the maximum thing is what? There's no limit. So sysgen's not gonna correct you and say, oh, you can't set that higher than. So I would like to see VSI either raise the maximum, which would be the optimum, because our systems these days have enough memory, we could probably afford to have some larger values. Or in the interim, at least change the maximum to 65,535 so that sysgen won't allow you to set a value that's going to get an unexpected result for. It's usually the number of modulo 65,536 is going to be something smaller than you intended. All right. On your math could be 1, that's right. But you wouldn't likely set it at 65,537. But yeah, that's the worst case. That's the worst case. Usually you set it to something like 80,000, which is a small, 15,000 per month. All right, each additional unit of ACP cache uses one 512 byte page of additional memory. And these days, even if you set all of these to the maximum setting of 65,535, and we have a number of customer systems where we've adjusted this over time to try to raise the cache hit rates, and we just bump into the maximum and run at 65,535. Even if you do that, that's only 32 megabytes of memory. I've been around long enough to know that that was total memory on some systems when I started, but these days it's a drop in the bucket. So even if you were at the maximum of 32 megabytes, you're not wasting a lot of space. And this is page space, so if you need the memory, the physical memory, you can page it out. All right. I like to assume that hit rate increases. I'm optimistic. I'll assume that hit rate increases will be proportional to the size of the cache increases. So if I see a hit rate of 50%, I'll double the size up to the maximum of 65,530. And if you see a hit rate of 80%, if you increase the cache by 25%, my rule of thumb works out reasonably well to, and the next time you run it, if you find that you need to increase it a little bit more, that's fine. This keeps you from making outlandish increases. It seems to be a reasonable rule of thumb. You can iterate over time. If you only get to reboot your systems once every 2 years, you can raise it higher than that, and it's not going to hurt anything. If you reboot every week, you're probably not going to be needing to be as drastic in the changes. All right, ACP FID cache, ACP EXT cache, and ACP Porta cache are per volume caches. That means that VMS is going to allocate that much space for every disk volume on the system. So the amount of memory that is used is going to be multiplied. If you increase it, it's going to be multiplied by the number of disk volumes. And we find that customers typically don't modify those. They tend to be okay without that. Yeah, we don't find them to be modified much in practice, but the others are often useful to modify to improve performance. Okay, RMS. Oh, this is an area. I wish Hein was here this time. Hein Vandenheuvel, he's sort of the master of this. RMS file tuning can often greatly improve your application performance, like huge orders of magnitude differences in performance. Often bucket sizes, you go look at a bucket size, it'll be a bucket size of 2 blocks or 3 blocks because it hasn't been set since 1980 or something. Bucket sizes can't be huge, as maximum of 64 blocks now, but often those are just tiny little things, so you're going to be doing tiny little IOs. Files may be converted only infrequently, so they can, or never. That's very possible. I'll often go on a customer system, and the sysUF has never been converted since the system was installed. That, if you don't convert the file, that leads to lots of revectors as you rewrite records. You've got to put in an RRV there, pointing someplace else. If you're writing based on a timestamp as a key or something, you may have lots of blocks at the beginning of the file. They're empty because those records have been deleted. You got to read through all of those sequentially to get up to the beginning and the first record in the file. Those sorts of things are helped by converting the file periodically. Long duplicate key chains in an alternate key is also something that we find often creates huge performance problems. If you've got a huge file with a large number of alternate keys where there's a duplicate value. VMS has to go sequentially through that whole chain to get to the end to stick the record there at the end of the duplicate key chain. So if you can make a null key, that can help a lot. Where it's a value like 0 or blank. At least detecting that will let you know, well, that's going to be painful. Maybe I ought to have data in global buffers. So when I have to read all of that whole chain, it's already in memory. Hein van den Heuvel has a freeware program called RMS_TuneCheck, and it's a wonderful tool. It'll give you a lot of these warnings about long duplicate keychains, files not being converted, tiny bucket sizes that result in deep indexes. So that's a very useful tool to pick up off the web on the freeware collections.
So one I use is RRV, which was on a deck article many years ago written for VAX, which compiles for Alpha. It also compiles for Integrity. The nice thing is you can feed it a wildcard on the disk, and it goes to every file on the disk, and the files can be open. You can still, it just gives you how many buckets, bucket size, how many revectored records. It's extremely simple, but it's quick.
Very useful tool.
Yeah.
And that was this tool?
No, it came out of a deck article. You know, when you had DSM,
Okay.
and there was the article, and it had this little bit of code on it. It's literally only that thing.
Okay.
I have no idea whether I've kept a copy of it.
What's it called?
It's just an RRV tool.
Okay.
We'll have a conversation, and maybe we can make it available publicly.
Okay.
You know, but it's originally digital.
I can tell you that all the articles that were in DSM link copied into not CSV tools, EARS, which is another article system that we had at DEC. And all of those were salvaged by DSI at the closure of HPE's business. They're not publicly available, but you can probably ping somebody like Debbie, because I know she was really involved. Actually, Gail Davidson, she's there heavily involved. So all the articles, over 20,000
Yes,
articles were saved.
Okay, that's interesting to know.
But it's all in a file of the MS box, almost like a note file that way. So completely different.
I've sometimes even stumbled across those articles in a Google search.
Sure.
Somebody has scrolled one away.
Sure.
Bless their hearts. That's appreciated. All right. Now RMS can readily cache files that are open for write on multiple nodes in the cluster, so it can do that better than XSC. So it can move down to the RMS level and cache that. RMS local buffers, often people don't have enough of those. They are private to a process. Now they may, if you've got a lot of processes reading the same file, they may contain the same data blocks from the file, but they can't share them because they're a local buffer. RMS global buffers, on the other hand, they can be shared and available to any process on the system. So by putting data into global buffers, you may actually save the total amount of memory that you're using to buffer those. Plus, you only have to read it once instead of once per process to be able to read that. The other thing that RMS global buffers help is that because of a change in algorithms, data that resides in global buffers requires fewer lock requests to access. Basically, they read the data into the global buffer, they set a blocking AST on it, and if anybody else needs it, then, I'm sorry, if anybody else needs it, they can go ahead and look at it. You don't have to take out another lock request because it's in the global buffer. If the buffer ever changes, the blocking AST then fires, and that'll result in an update of the buffer. So I have some customers that actually will put RMS global buffers onto files strictly because it reduces the lock rate for their cluster. And it has nothing to do with, I mean, it'll help the IO as well, but that may be their primary motivation to reduce the lock rate. I'll look at some clusters and sysuf.dat has no global buffers on it. And yet across the cluster, people are doing 1,000 block requests per second to this RMS file lock for sysuf.dat. And just by putting some small number of global buffers on that thing, you can cut the lock rate down significantly, because that's just overhead. And it doesn't take much memory to put a few RMS global buffers on sysUAF and LightSys. What I did find is that if you're doing IO to an index file in DCL, unfortunately, process permanent files like the file streams in DCL are not helped by RMS global buffers. I kept suggesting that we make an improvement to one of our tools, and Norm kept telling me, Keith, that doesn't work in this case. So now I will probably remember it. One of the big questions people have is, how many RMS global buffers shall I put on a file? What Hein van den Heuvel used to say is, the only wrong answer is 0. So if you have at least one, that's better than 0. And here I have an example for sysUAF.dat. Set file sysUAF.dat/global equals % equals tens, and also enabling statistics at the same time. And if you do /share, you can change that while the file is already open somewhere in the cluster. So this will say, allocate a number of global buffers equal to 10% of the size of the file. Could be 50%, could be 100%, whatever percentage you want. I find that turning on RMS statistics gathering at the same time helps, because then you can use monitor RMS /file equals whatever the file is. You can look at various items, how many operations of IOs are you doing per second, what are the data rates, what are the locking rates, what is the caching, how effective is the caching in the RMS global buffers. Once you turn the statistics on, you can see all those statistics. It's a little bit more overhead, but not a lot. I find it's worthwhile. Thanks to changes in OpenVMS over the years, lookups, which used to be sequential, are now hashed, so they're quicker. And also the data as of 7.2 resides in S2 address space. So with 64-bit address space, you've got lots of space. The counts can now be over 16 bits in size. You can use larger numbers of RMS global buffer counts, and it's less painful than it used to be in ancient versions. If you get somebody that says, oh, you know, I looked at RMS global buffers 20 years ago, 30 years ago, and it just didn't work out for us, chances are the reason that it didn't work out well for them then has gone away. So it's something to consider again. Downsides. Oh, no, this is a good side. LCK show active. This is something that's really useful to me in finding hot files within a cluster if they're hot RMS index files. LCK show active gives you a list of the hottest files in descending order by lock operation count. So you can look at the top of the list and see what are your files that you're hitting the worst. And maybe those are the ones that are the best candidates for RMS global buffers. And then once you put RMS global buffers on them, they tend to drop down farther in the list, and you can get the new heavy hitters at the top of the list. One thing to watch out for is this activity field is 16-bit. So if you see a value like 65, 65, something short, just short of 65, what you've done is you've picked the speedometer on that counter, you've maxed it out, and I think it's 65 to 80 or something like that. That just means that you've had more block requests than 65, 5,035 per 8-second remaster scan. So you know it's a busy file, you just don't know how much busier. Anyway, so start at the top of that list, add RMS global buffers to the top RMS index files in the list, and then reiterate until you get rid of a lot of block operations in your cluster. And this will also help the IO efficiency as well, since those RMS global buffers will be helping in terms of the actual IO statistics as well. The one downside of global buffers is they have to be mapped into memory where the files are. I added RMS global buffers to a system once. This was a stock traded system. Very early on, when they were doing maybe 30 trades a day at the stock brokerage, they decided that they wanted all the files to be open at night when they did backups. Excuse me, they wanted all the files to be closed at night when they did backups. And since they were only doing 30 transactions a day, they would open the file on every transaction, do the IOs, and then close the file. That worked fine when they were doing 30 transactions per second, but that code didn't get changed. So by the time I got there, they were doing 15,000 transactions a day. And I turned on RMS global buffers, and that created a lot of overhead because every time they opened the file, they were having to map the RMS global buffers. And every time they closed it, they were having to unmap it. That makes the memory management spin lock go crazy. And we ended up going back to the developers, and they changed the code so that the file could stay open during the day. And that improves the efficiency of their system. But that's one thing to watch out for if your file is being opened and grows rapidly. Yes, sir.
I was also gonna say that if the file is open share, then another option would be another process goes and opens the file, because it keeps the file from being open.
And then the good point,
Buffer say,
and the global buffer will stay in memory because there's at least one process on the system with it. So just have the process open the file and then go into an infinite wait until the system reboots. And then the next time it reboots, have that program run first thing to open the file. Excellent, excellent.
We do that.
of course, we'll open the file 50,000 times a second. Precision, correct the applications.
Yeah, you can fix that, but at least it would help. I mean, it will still have to be mapped into that application, but it will not lose the contents of the global buffers between the open and close. It'll preserve those in memory. All right, sysgen parameters that are relevant to global buffers, global sections, global pages, global page file. I find AutoGen seems to do a pretty good job on global pages and global page file. Global sections, I like to keep some reserve, especially since that's the one that requires a reboot to change it. It's a static sysgen parameter. Now you need one global section unit for each file, whether that file has some number of global buffers enabled or has statistics gathering enabled. And if you have both global buffers on it and statistics enabled, it still only uses one unit of global sections. So if you're expecting to add RMS global buffers to a lot of RMS index files, you probably need to check to see how many of the global sections you have free. And the lexical function $get SYI, you can say free underscore global sex SECTS and tell how many free global sections there are in the system. There's a sysgen parameter RMS underscore SEQ FILE underscore WVH. So that's a sysgen parameter that enables, if you set it to 1, or disables if you leave it to the default value of 0. RMS right behind as a system default for any unshared sequential disk files if the file is open for image IO with write access specified. So this would typically be stuff writing 512 byte blocks. So that can provide you with some performance improvements by default for those across the whole system. So in a lot of our customer systems, we have this trick. We talked about write back caching if you can risk it for those sort and merge work files, for example. Here's a way to set a SCSI disk, or it could be a SAS disk, to write cache enable. So you use the SCSI underscore mode program from system, etc. Name, specify device. Run through this. Do the SCSI mode for this device. AJ offset. You're setting the particular caching parameters value to there. And, that will allow you to turn on write back caching for that storage device and get a little bit of performance for that particular SCSI device, if that's data that you can risk in terms of a power film. And that's the material that I had for you today, which we went through in plenty of time. Any questions? Yes, sir.
That last item, is any of that mitigated by the fact that most of the modern controllers and everything have like battery backup cache, or you're still at risk because the actual storage unit that you're mapped out to.
Well, I don't think you can reach the individual disks through the storage controllers. I think this would be for local storage disks. If it's a fiber channel disk behind the controller, I don't know if we'd have to play with it to see if that's something that we could, characteristic that we could even change.
Or some of those modern storage SAN controllers, even going back to like HSGs or on power loss would flush the cache and write the disk.
What they did was they had battery backed cache. So that if you had a power failure, the data would still be in the cache with all the structures to be able to locate it. And when the controller rebooted, it would come up and say, oh man, I've got some uncompleted writes. And I need to write to these disks, these blocks with this data. And so they would do it because the battery, the cache was battery backed. On individual SCSI disks, they have cache and they can turn on this feature, but there typically is not battery backup. So on a power failure, those cache blocks go away. So that's the danger in doing this on local SCSI disks that we don't have on a controller with battery backup cache.
Just maybe interest for anybody that has or had EVA controllers. The cache in there is lithium cells, the 1850 cells, and one of our clients who declined hardware support, they bought a unit and then rebuilt it, and inside is a whole
Massive cache.
managing electronics. So this replaced the cell with temperatures on it, there's a huge amount of logic in there. But obviously with it being lithium, you've got to be careful about constantly charging them. It's quite interesting to see inside them, and we've just described like they are. That's what's in it. Obviously the high quality cell, but interesting to see. And the EVA, that maybe explains why it was so expensive to replace the things.
Perhaps so. All right. Well, have a great day.
Thank you.